Yeah. Okay. Yeah. Okay. So this talk will be about tellurium. Tellurium is a very interesting material. It has a very strong spin-orbit coupling, which is the reason why it is one of the major building blocks for many topologically interesting materials. Here it's about elemental tellurium. Elemental tellurium has quite an interesting crystal structure, as you will see later. And it has a very particular structure of the valence band, which is this camelback structure, which is around one of the high symmetry points. And these two maxima, they lie very close together. And this leads to a situation where the acceptor levels, where the acceptor level actually splits into two acceptor levels. And when you apply pressure on the system, then you change the band structure, and then it becomes one maximum, and then you have only one acceptor level. At the same time, due to the spin-orbit coupling, you have a very strong spin-orbit. You have a very interesting spin texture. So on this maxima, the spin is oriented in the contrary direction than on that one, while in this configuration, you have a configuration where the spins are pointing in all directions. And this is something like a transition. I don't know if you can call it a quantum phase transition, probably not, but it reflects itself in certain physical properties, and that is what this talk is basically about. These are the collaborators who are involved in the project. Specific attention should be given to Jaime. He is a PhD student whose project that is, so he has done a huge part of the work, and we have many problems in Rio at the moment with helium. We have a terrible situation, so he's currently in Cambridge, where he finishes these measurements, because we don't have helium since a year, and that means that this project is not really finished, but we have some presentable results, so this is what I will show you here now. So we start with the crystal structure, what I was talking about. The crystal structure is trigonal, but it is a bit different from trivially trigonal. You can see that in the AB plane, the tellurium atoms have three different positions, so you have 3 atoms per unit cell. And if you look how they are stacked in spirals, and so your tellurium crystal has a chirality. You have right-handed and left-handed tellurium, and they actually have quite different properties, as you will see later. The lattice parameters are 4.5 angstrom in this direction, and only 6 angstrom in this direction. So you can see these bonds here are very strong. They are of covalent type, while at the same time, these here are weakly van der Waals bound. And this creates a situation which makes it a bit difficult to find proper approximation for DFT calculations, for example. So when you look through the literature, they are literally all over the place in many respects. I will talk about that in a minute. A more practical consequence is that they are very brittle, the crystals, so it's not too easy to work with pressure with them. And then there is a fun fact about tellurium, which has nothing to do with anything else I will tell here, but it's so cool that one really has to know that, and that is, so tellurium has quite a low melting point, but these chains, they don't melt so quickly. So when you melt it, then you create a string liquid before you create a normal liquid, and this is very rare in nature. So let's go back to the crystal version of tellurium. Tellurium in the form that I just showed you is a semiconductor with a gap of quite a small band gap with 320 millielectron volts. And the band gap is almost direct. And that was exactly what I was telling you about before. So it's actually here this camelback structure around the H point that makes the band gap almost direct. And this structure is obviously due to the spin-orbit coupling. And this also gives a reason for the spin texture, which you can see here. So depending on if you have left-handed or right-handed tellurium, either the spins on this maximum point along the c-axis or anti-parallel to the c-axis. And that means when you apply a current through tellurium along the c-axis, you magnetize the material in the direction of the c-axis or contrary to the direction of the c-axis, depending on the chirality of your material. And this is something that currently many people think might be important for future applications. So why is the valence band so important in tellurium? That is because naturally tellurium forms vacancies. Those people here who worked with tellurium and tried to grow crystals which contain tellurium, they probably know that. And these vacancies, they serve as acceptor levels, as acceptors. And therefore your tellurium is always p-type. So these are a few of the curves from samples that we have grown, and they all show extrinsic behavior. And that is like the normal thing that you find all over the literature. You will never find a really beautiful intrinsic semiconducting curve from tellurium. As I said, due to this camelback structure, you create these two acceptor levels, and they are called bonding and anti-bonding level. That is a bit of a confusing name because the vacancies, of course, they don't bond to anything, but of course it's based on the fact that one of the two levels has the probability density maximum around the position of the vacancy, and the other one has a minimum at the same position. So when you apply pressure on the material, then this band gap narrows, and at the same time, the valence band changes to this one maximum. And these both properties, they have been shown experimentally. So that you have quantum oscillation measurements which show this, and the narrowing of the gap you see too. However, for reasons that we were not aware of, the pressure range between 15 and 30 kilobar is not studied so much, which is very strange. So at 40 kilobar, you have a structural phase transition to the monoclinic lattice, but it is now in DFT calculation generally, they predict that the gap closes between 15 and 30 kilobar, so it's quite an interesting area to study. And what happens then, that depends very much on the paper. So there are people who say that you will get into a metallic state, you will have a normal insulator to metal transition, and there are other papers which suggest that it would become a topological insulator, and there are other papers which suggest it becomes a wire metal. So it's definitely something that is worth to be studied, and that was our original motivation. As you can see, that is not in the end what my talk will be about, but that was our original motivation. We are actually only aware of one study that is in this pressure range that focuses on a completely different topic and is also at really high temperatures for our, in comparison to what we do usually. So we thought that this might be a good idea. And to do that, we already had some experience with tellurium due to other projects, but we heard that we can have tellurium with very few vacancies from Princeton Scientific, so we bought a crystal, and then we cleaned the surface chemically, and then we put it into a 30 kilowatt piston cell. As a cooling device, we used an adiabatic demagnetization fridge, and then we performed resistivity and low field magnetoresistance measurements. We would have loved, actually, I mean, of course, we tried to make Hall measurements too, but these samples are so brittle that when one of the Hall contacts broke, which we have some experience with, we decided that we measure first to the high pressure, then we open the cell again, and then we measure Hall. However, as I've told you before, we have this problem with helium, so that you won't see any Hall data from us here. The current direction is perpendicular to the C direction, which is in parallel to the direction of the external field. And here you can see the resistivity curves, and you can see that up to 20 kilobar, you have semiconducting behavior. And actually, you see that these are obviously extrinsic curves, but we have very few vacancies. They are quite good. And above 200 Kelvin, depending on the pressure, we have actually a good way to extract the gap size. We have a good intrinsic behavior in that area. And when you extract the gap size, then you can already see that we expect the gap to close after the transition to the monoclinic phase, so that was not a success. However, early in our experiment, we found an anomaly that is accompanied with a strong change in the slope in the resistivity curves. And then we looked through the literature, and we found that in all samples with a really high quality, with very few vacancies, you see something like this, and it has also been studied a little bit in this paper, but the explanation is quite is inconsistent. But anyway, so this anomaly shifts to higher temperature when we apply pressure, and at about 20 kilobar it just vanishes. And at the same time there appears a second anomaly, about 16 kilobar, that also shifts up with temperature. So I should mention this paper here at this point. These are the samples that we know of from the literature with the highest amount of vacancies that do not have chemical dopings, and they become around this range here metallic. So in zero pressure, this is at 1 Kelvin, this anomaly. So we analyze this slope here, and what we find is that this follows very well the exponential of 1 over t of 1 to the 4, so that is probably variable range hopping, and that is, as I have shown off, with the quality of our sample. So obviously this is not from the this is from the vacancies, which is the only thing that has a certain amount of disorder. And then we find a resistivity saturation, which probably means that the Fermi level lies within the impurity band. This has a very, if you look now, if you associate this temperature here with the saturation temperature, if you look at this over pressure, you see that it has quite a peculiar, it develops in a peculiar way. So it almost goes to zero here, and it starts here from relatively high, then it goes up quite quickly. And at the same time, when you look at T0, then you see that it actually peaks around that area, and then it drops. And you would think now, if you extrapolate this, and this is only a guide to the eye, this is not in there, then you would think that probably the mobility edge is reached at about 24 kilobar. So there's something here that is in favor of localization, which suppresses the metallization of the material. And as I have mentioned before, we would expect now that we have this transition from the orbitals of the vacancies. So we have these two acceptor levels, and this is not from us. I mean, we did it for this paper. This is basically you can make an effective, if you have an effective Hamiltonian with the band structure, and then so this is now the band. This includes the band, the upper valence band, and the band below, because when you increase the pressure, then you increase the spin orbit in between this to this. And then you use a trial function with these two with a hydrogen like function here in these two terms, and then you get this bonding and this anti-bonding level. And on the other side of the transition, you should get something like a hydrogen-like level with an anisotropy, because you have a different dielectric constant in the z direction than in the AB direction. At the same time, one might expect that at the point of the transition, the effective mass actually increases quite a lot, simply for geometrical reasons. And then, so at the transition itself, we expect actually that there is a higher, that the effective volume of the orbitals is much smaller than on both sides of the transition. At the same time, and no one here can read these graphs. I needed a long time to understand them, and we didn't have time to make a nice picture for that. But we performed some DFT calculations on the spin texture, and we find that the spin texture actually changes. This is this famous spin texture that has been discussed a lot in the literature, and then it changes to this type of spin texture. And then you would also expect that you maybe get some, so we have a highly disordered metal from the vacancies, and then you would probably expect something like localization, and that should be visible in the magnetoresistance curves. So these are now the magnetoresistance curve up to below 15 kilobar, so before we actually have the transition. And we see that these curves here, they have generally a negative magnetoresistance. So in the literature, the magnetoresistance of tellurium is extremely sensitive to doping. But for samples which are not doped, you at ambient pressure usually have a positive magnetoresistance. So here we can see these are all negative, but the one for the lowest pressure that we have measured has still this positive slope. And when you look now at very low magnetic fields, and you see this little feature here, which looks a bit like a weak anti-localization feature, but you wouldn't expect that you actually can describe that very well with a normal approach for weak anti-localization, because you have these two spin directions, which are actually not like you have it in other materials where you have all possible spin directions present. And then, after the transition, the magnetoresistance changes quite drastically, so you can see now that it is quite flat in comparison to this. It's still negative, but it's quite flat in comparison to the curves before. And you see now at low fields, you actually have a much stronger feature here in the magnetoresistance that looks like a weak anti-localization. And if you now use this, we use as a fit, so we have basically the dephasing term plus a spin-orbit interaction, and then you see that this actually gives a very good fit, however, only for high pressures, not for low pressures. And for high pressures, we do not know how to fit this curve very well. So however, when we give a description of how strong the spin-orbit coupling is, we do it just by checking the resistivity maximum. And then when you see the resistivity maximum, it's going down again. And then actually these fields, they are a bit like all over the place here. But I put these green lines in here so it looks a bit nicer. And when you see then how they behave with temperature, then you would expect them to actually fall off with 1 over T. That is not the case so much, maybe a little bit, but we do not know yet exactly if that is a dependency that we would actually expect. So yeah, I give the last talk today, so you will be very happy to see that I was very quick in talking. So that is, so we studied the resistivity and the low field magnetoresistance behavior of our samples, and our data suggests that there is no gap closing, which is something that has been discussed a lot in the literature recently. And we found this anomaly, which actually shifts up with pressure, and a second anomaly that appears while the other one washes out. And so this is probably associated to the change in the band structure from this double maximum to a normal band maximum, and therefore probably to the orbitals that are associated with the acceptor levels. And this manifests itself in some characteristic quantities that we have measured, and we can see that the magnetoresistance changes quite drastically, and that is probably due to the change due to the spin-orbit coupling. Yeah.